Hi, welcome back to a new unit in our Algebra 2 course. This unit is all about functions. We will do a little bit of review of linear functions as well, but mainly I want to talk about function theory because it's going to be at the heart of almost everything you'll do in mathematics. Our first lesson is just about functions in general. A function maps each element in the domain to exactly one element in the range, also called codomain. The domain of a function is the set of real number values for the input, which results in a real number output. Remember, real numbers in, real numbers out. So our domain can be limited if a certain number, when you put it in the function, results in a non-real output. Remember, we require real numbers to go in and we require real numbers to come out. Let's take a look at an example of some functions that you could encounter. Okay, so we have a function here that's mapping from a domain of X to a domain of Y. Well, actually, I'm getting ahead of myself. That's the instructions, actually. We're supposed to decide whether or not this is a function. Y as a function of X. So in order to be a function, every value of X has to be mapped to a unique value in Y. Or excuse me, a single value in Y. Every value of X needs to be mapped to a single value in Y. But you can see here that negative 5 is being mapped to two different values in Y. That's not allowed, right? So this is not a function. We're going to say Y is not a function of X. All right, let's take a look at another example. All right, on this one, we need to remember that the y coordinate is the second coordinate in a point. So this here is x, and this is my y. So you can see that we have 1, 3, and 5 for the x values. And they are being mapped to 2. So 1 is being mapped to 2, 3 is being mapped to 2, and 5 is being mapped to 2. And that's okay. I misspoke earlier, but in a function, you don't have to have your x's mapped to different or unique y values. We just need to have each x mapped to one number. So here, my x's, each x value is mapped to a single value. It happens that each x value is mapped to the same one, but that is totally okay. This is a function. Specifically, y is a function of x. All right, let's take a look at another one. All right, I've got this kind of scatter plot here, and let's make a chart. All right, so I've got x values, it looks like at negative 3, negative 1, 2, and 6. Those are my x values, and where are they being mapped? Well, they're being mapped to, let's see here, negative 3 is going to negative 3. Negative 1 is going to 3, but also to 6. 2 is being mapped to 0, but also to 3. And then 6 is being mapped to, I think that's an 8 over there. So you can see, though, that we do have two values here that are being mapped. Two values of x that are being mapped to more than one y value. So this is, we cannot say that y is a function of x. Y is not a function of x. And what we're going to say in general is that if a function fails a vertical line test, if I could draw a vertical line that passes through the graph more than one time, then there must be an x value that is being mapped to more than one y. So we're going to say that this function here, you may have heard this before, we're going to say that it fails the vertical line test. All right, you've got some practice problems to do. Give them a try. Pause the video, please, and then we will go over the solutions. All right, let's see how we did. All right, for this first one, it looks like each x value is being mapped to one specific y value. And when we have tables of data, or when we have ordered pairs, in general, we can say that if the x's don't repeat, then each x must be mapped to only one y value. So since the x's don't repeat, we're going to say that y is a function of x. All right, so let's use that in mind. Let's see about the x values here. 0, 1, 2, 3. They must each, since they're only listed one time, there's no possibility that there's an x value that's being mapped to two different y values. So we're going to say y is a function of x. All right, now if I were to use a vertical line here to test this, you should see that there's never a place where I could draw a vertical line that touches this graph at more than one place. So this, again, is going to be y is a function of x. But on this one here, there's actually many, many places where I could draw a vertical line and fail the vertical line test. So we're going to conclude that this one is not a function because it touches the graph at more than one place. So y is not a function of x. Okay. Right, so an important part of understanding functions is to be able to determine what is the domain and the range of the function. So let's take a look at an example where we do that. So I want us to determine the domain and the range of each one of these functions. The domain is the set of real numbers for the input that result in a real number for the output. And unless it's otherwise stated, we're going to say x is our input and y is our output. So my domain on part A, it's a discrete set. I'm going to just describe it by listing the values in set notation. They're -1, 3, 4, and 9. And I'll describe the range in a similar way. 10, 20, 30, and 40. And you can try and put these numbers in order from least to greatest because it makes it look pretty. It doesn't matter. They don't have to necessarily line up like these do. You just need to list them, but make sure you don't list any repeated numbers. If you have repeated y values, which is allowed, you only list them once. Okay, let's take a look at the domain here. The domain is the x coordinates, so 0, 1, 2, and 3. And the range is 10, 20, 30, and 40. All right, let's look at this one. Let's do the domain. And we can use set builder notation, or we can use interval notation. But we can't just list numbers because this is an infinite amount of numbers in any one place. This is a continuous function. There's an infinite number of points in any one place, even if I didn't have these arrows. But because these arrows are showing me that the graph is going to continue going down and to the left and up and to the right, we're going to make a conclusion that the domain of this function is negative infinity to infinity. Or we could do the symbol for all real numbers. The range is also going to be negative infinity to infinity. All right, let's take a look at letter D. On this one here, we definitely have some endpoints here, and it's important that we see that those are closed endpoints, so we expect brackets. Let's use our domain here. My domain is from negative 1, 2, 3, 4, 5, 6, negative 7 to 1. And they're included, so we'll do the hard endpoint there. And the range, now we need to, if there's no dot at all, you can assume that's a closed endpoint, and we're really just estimating here. We would need an equation to be exact, but it looks like the range of y values goes from 2 to 7. So we're going to say that our range is 2 to 7. Okay? All right, I think you now probably have a practice problem to do. So pause the video and do practice 1.2. All right, let's see how we did. For part A, the domain here is 100, 50, 25, 0. The range is 1, 2, 3, and 4. Oh, looks like I gave you the same problem again, didn't I? Oh well. That happens. The domain is 0, 1, 2, 3. And the range is 0, 1, 2, 3. Oh no, it looks like the same problem, but that's a different problem. Okay, never mind. Same x's, but they were different y's. All right. Let's take a look at letter C. Okay, so what's the domain here? Well, because of the arrows, we can say that this graph is going forever to the left and to the right. So it would be negative infinity to infinity, or all real numbers. And the range, well, we definitely have a lowest point of a y value of 0. So you could either use set builder notation and say y such that y is greater than or equal to 0. Or you could just say 0 to infinity. Both of these answers are correct. All right, let's take a look at the next one. My domain is 3, 4, 5, 6. What do y'all think? Is that 6? Looks like negative 6 to me. And then 1, 2, 3, 4, 5, 6, 7. This looks like positive 7 over here. Don't worry if you miscounted, or maybe I'm miscounting. We're just doing this to get a feel for it. And let's take a look at the range. I'm going to make my graph with a different color here. I'm kind of estimating there. It might be a little below negative 3. We'll say negative 3. And this is 1, 2, 3, 4, 5, 6. Oh, you know what? Did you catch it? I just realized something. This point is not closed. I hope you did this. I hope you put a parenthesis around that 7. Huh? Okay. And then my range is going to be parentheses negative 3 to 6 with a closed there. Be careful about that. I fell for that trap, didn't I? There's no colored in there. That's not closed. That's open. So that we say the graph gets infinitely close to this point at 7, -3, but doesn't actually include it. All right. I think we just got a little bit of vocabulary we need to clarify here. So let's go over that together. The domain of a function can be explicitly stated or implied by the function's equation itself. For example, the function y equals x plus 5 for x greater than or equal to 0, we're going to call that an explicit domain of x is greater than or equal to 0, because whoever is writing this function for us to use has explicitly directly told us that this function is only for x greater than or equal to 0. I'm not sure why they've chosen this domain. We would have to know the situation. It could be that for negative x values, it's just quite simply x plus 5 does not match the data or make proper predictions. But for some reason, they've limited the domain that way. Now, on the other hand, we could also have a function with an implied domain that is limited. And the implied domain is that domain that the equation itself requires in order to give real number outputs. So when you look at the equation y equals the square root of x, we know that the domain is all of the x values that will result in a real number output. So real numbers have to go in and real numbers have to go out. But if I were to put in, say, -1, which is a real number, the square root of -1 is not a real number. So just the equation y equals square root of x, I don't have to explicitly say x greater than or equal to 0. It is implied. Implied means to be stated without saying, right? It is this equation right here implies the truth that the domain is x greater than or equal to 0, because those are the only real number values for x that result in a real number output. So that can be something that's very challenging for a lot of students when they are asked to find the implied domain, because you have to think about the real numbers that cause problems. So let's take a look at it. State the implied domain of each of the following functions. Explain your reasoning. Well, basically, there are two things that we have learned that we don't do in this class. We are going to add another one later in the year and make it 3. But really, the two things we're going to not do is we're not going to even root, 4th root, 6th root, whatever, but I'll just say square root. We're not going to square root negative numbers. These are no-nos, okay? And we're not going to divide by 0. So if we see either one of those things happen, we know that that is not a real number. So let's take a look at this equation with that in mind. I don't see any square roots, so there's not any problem there, but there is a division. And so when I look at the division, I need to think, well, is it possible that there's a real number I could plug in for x that results in me dividing by 0? Well, in this case, I think it's pretty obvious that if we plugged in 0 for x, we would get 1 divided by 0. Are there any other numbers besides 0 that could cause us to get a non-real result? Well, like we said, there's no square roots, so don't worry about that. And I think you'll believe me that 0 is the only number we could plug in for x that would cause that problem. So I'm going to say that my domain, my implied domain, but I'll just say domain, is all real numbers except 0. Now, that's kind of a lazy way of writing it. I could put it in set notation, but I want the concept to be important, so I just tell my students to write that. There are a couple other ways I could state the answer. I could say negative infinity to 0, union 0 to infinity. Notice that I did not include the 0. There's a parenthesis, so this is all real numbers 6, 0. But I think that's easier, right? We could put in set notation. We could say x such that x does not equal 0. And that works as well, but usually with these I just say all real except, which is fine. So any one of these ways of saying it, any one of these are acceptable, but I will tend towards this one. All right, let's take a look at the square root one now. Well, we don't see any division, so we don't have to worry about the divide by 0, but we do have a square root. So are there numbers that if I put them in for x, are there real numbers that if I put them in for x would result in a negative number that I'm trying to square root? Well, because it's a negative x, any positive x value, when I plug it in for x, is going to give me a negative number in the radical. For example, if x equals 4, we would have this y would equal the square root of negative 4, but that's not a real number, so that's not going to work. But if I plug in negative numbers, the negative on the outside will cancel out that negative and make it positive. So for example, if we had x equals, let's say, negative 9, then y would equal the square root of a negative of negative 9. But two negatives make a positive, so that'd be 3. So it's going to turn out that as long as our x's are negative or 0, because we can square root 0, that this is fine. So I'm going to say that my domain is negative infinity to 0, including 0. What's another way to write that? Well, you could say x such that x is less than or equal to 0. Both of those different ways of saying it are completely acceptable. All right, let's take a look at letter C. Y equals x squared. Well, there's no division bar, so we don't have to worry about dividing by 0. There's a square, but there's no square root. And you can square any number. So any real number I put in for x is going to result in a real number for y. So that my domain is either negative infinity to infinity, or you can just say all real numbers, because there's nothing that causes any problems at all. I think we have one more example, and this one might require us to use a little bit of thinking. I'll just clear this whole thing out, actually. So I have the square root of 2x minus 7. Well, what I need to do here is I need to set up an equation that I can use to figure out what I can't have. We know that we cannot square root a negative. So I'm going to solve for the requirements for what 2x minus 7 must be. 2x minus 7 must be greater than or equal to 0. Now, please keep in mind, this question has nothing to do with me solving for x or anything like that, but yet here I am solving an inequality. I'm doing it in order to answer the question, what is the domain? What values of x make for a real y? That's the question. And we know that whatever values of x cause this portion under the square root to be greater than or equal to 0 is going to be a-okay. And I can use my algebra to answer this question. And what I have found upon solving is that all x values that are greater than or equal to 7.5 will result in a real number. So I'm going to say that my domain is x such that x is greater than or equal to 7 over 2. 7 divided by 2 is about 3.5. So what we're saying is that if we were to put in a number like 3, we would not get a real number output. So let's try it. Let's see, because this shouldn't work. This should not be in our domain, right? Well, I would have to do 2 times 3 minus 7. But that's 6 minus 7. That's negative 1. That is not allowed. So you can see that's not going to work. But on the other side, on the other hand, if we were to try x equals 4, 4 is bigger than 7.5. So according to what our domain is saying, that should work. We should get a real number out. 2 times 4 is 8, and 8 minus 7 is 1. Well, now I'm taking the square root of a positive 1. That is a real number. So that's kind of how that works. All right, so that's the implied domain, and it can be tricky at times. Let's take a look at explicit domain. Explicit domain is not always easy to get one right answer. Sometimes it's a little bit debatable, but what's important is that you understand kind of the feel for it and why we have it. So usually it's in a problem situation. So for the following situations, we're going to state an equation and an explicit domain for the function to model the situation. So the math club can buy calculators for $50 each. So let's say that we had y was going to represent the total price, and x is going to represent the calculators. And we're going to work a lot in this unit on modeling situations like this, but we'll do it on a whole big lesson. So don't worry too much about it. As much as I want you thinking about how the domain being restricted explicitly makes this more meaningful. So the total price as a function of the number of calculators, the total price is 50 times X. For every calculator X, you cost you $50 more. So here's my question though. Can you buy a negative calculator? Well, I hope not. If we did, I mean, well, maybe you can. Maybe you're returning one. But I mean, if we were to order, call up a tech store and order negative 10 calculators here, well, I just got myself a cool $500 because now they're going to send me an invoice for negative $500, which means they pay me. So no, I don't think that's reasonable. So I'm going to say that my domain, I'm going to explicitly limit my domain to say that X has to be greater than or equal to 0, but also, can you buy a fractional amount of calculators? No, you can't. So I'm going to say X has to be an integer and X has to be greater than or equal to 0. Remember the double strike Z means integer. You could also just write out the word integer if you don't remember that, but the more you see it, the better it is. So we're saying that X has to be a non-decimal amount and has to be greater than or equal to 0. All right, the weight of rope is 0.25 pounds per foot of rope length. So if I let Y be the weight in pounds, and I'm going to let X be the feet of rope, then I can say that Y is 0.25 times X. Well, let's talk about the domain on this one. So, are we allowed to have negative amounts of rope? Well, no. Then we'd have a negative weight. So we know that X has to be greater than or equal to 0 for this function to work. But are we allowed to have decimal numbers? Well, yeah, absolutely. You can have half a foot or 2.3 feet. So I'm not going to restrict it to just the integer. I'm just going to say X greater than or equal to 0. So that's my explicit domain for those two problems. All right, so what I want you to do is to practice finding the implied domain, pause the video, and then unpause it when you're ready to go over and check your answers. All right, let's see how you did. Okay, so what numbers could be problems here? Remember, we're not allowed to square root a negative, and we're not allowed to divide by 0. Well, hopefully you see that X being 5 would cause this to divide by 0. So I'm going to say that my domain is all real numbers except 0. Oh, sorry, except what? Not 0. Except 5. It was 5 that caused me to divide by 0. And what about this one? Well, we know that this has to be greater than or equal to 0, right? So let's solve that. We know that what's under the radical has to be greater than or equal to 0. I'll just add the x to the other side, and we see that x has to be less than or equal to 5. Maybe we'll use interval notation this time. Okay, on this one here, I am dividing, but I'm dividing by 4, and there's no variable in the denominator. There's no chance this could ever cause a division by 0 error. Now, I can have 0 on top, I just can't have it on bottom. So, in fact, this is all real numbers. There's nothing bad that can happen there. All right, so now what I want you to do is to try and do practice 1.4, which is going to ask you to write an equation and then explicitly limit the domain if necessary. Okay, state an equation and explicitly define a domain for the following situation. To celebrate a recent victory, the math team's coach take the team to the sequel to the movie Pi. It's called Tau. Little math joke there. The cost to see, not the see, the cost to see the movie is $5 per person who attends. Okay, so $5 per person. So if we let y equal the cost, and we'll let x be the number of people, then I would say that y is equal to 5 times x. But I think you will agree that my domain needs to be limited to where x is greater than or equal to 0, and x has to be an integer. So you can say x is an integer. This little symbol, I don't know if I described that earlier. This is red, is a, r is an element of. It's just shorthand. It's like a sideways e. But you don't have to remember all those math symbols right now. I just want to expose you to them. All right, the equation for a function can be written in function notation. Which shows the input and output of the function at the same time. So for example, if we have y equals 2x plus 1, it can be written as f of x equals 2x plus 1. Well, I could also write it as g of x equals 2x plus 1. Or I could write it as f of n equals 2n plus 1 if I'm using a different letter besides x. But basically, you just give it a name and then show the input. Let's practice. Or let's example, I should say. Because this one's for me. All right, I have example 1.5. F of x equals 3x minus 5, and g of x equals x over 2. So f of 0, how do I find that? Well, this is the input. Whatever's there goes in for x. So this is 3 times 0 minus 5. So f of 0 must equal 0 minus 5 is negative 5. G of 10, same thing. We need to plug 10 in for x in the function g. Oops, that should be a 10. Well, 10 divided by 2 is 5, so g of 10 is 5. F of n, same thing. I need to plug an in for x, and you get 3n minus 5. Basically, just changing the variable letter. What about f of x plus 5? Well, I have to put x plus 5 wherever there's an x. So right here, there's an x. I get replaced with x plus 5. So it becomes 3 times x plus 5 minus 5. We could leave it like that, or we could even simplify. Distribute 3x plus 15 minus 5 gives me 3x plus 10. So f of x plus 5 became 3x plus 10. Solve for the following. F of x equals 16. Well, in this case, f of x is 3x minus 5, and we're solving it equal to 16. So I'm not plugging 16 in. I'm finding the x value that makes f of x have an output of 16. I'll add 5 to both sides, and I get 3x equals 21. Divide by 3, and I get x equals 7. All right, next I have g of x equals 4. So I'll do x over 2 is equal to 4, and multiply both sides by 2, and give myself x equals 8. All right, you have one more set of practice problems to do in this somewhat lengthy lesson. So give it a shot and pause the video, and we will go over them, and then we'll finish up. All right, let's see how we did. We have f of negative 2. So you should have put negative 2 in everywhere there's an x in f. Notice it has to go in parentheses. Otherwise, the negative wouldn't get squared. And the entire x is squared, and x is negative 2. So that's 4 minus 1, which is 3. G of 7. 7 minus 6. That's not too bad. That's just a 1. F of n. That is just a variable change right there. And g of x plus 6 is going to become x plus 6 replaces the x, and then we still have the minus 6, so it becomes just x. And now we solve. We replace g of x with what g of x is, the equation for it, and solve for x. Okay, the only thing left for you to do is just consider the exit ticket, which is your own. I want you to write a problem situation where the explicit domain for the function model would be the set of whole numbers. Explain. And then write one where this is a domain of all real numbers greater than or equal to 5. Ooh, see if you can come up with that. Good luck, and until I see you again, take care.